Good morning. Welcome back. Hope you had a lovely Easter. Missed opportunity. I should have made an Easter themed test. Oh well. It's hard. I should have. Today we start probably the most fun chapter that we're going to see. It's mostly fun just because we've worked so hard with inference, right? With hypothesis testing and confidence intervals. And sure, we'll kind of touch on some of that here, but that's not the main event of what we're talking about in chapter 8. Chapter 8 is called An Introduction to Linear Regression. Just want to break this down. So linear means a straight line, right? And so a straight line. What are some things we already know about a straight line? We know the equation of a line, probably from, I don't know, math 8. I don't know. Y equals mx plus b. Might have been a while, but oh, that sounds familiar, right? We use some version of y equals mx plus b, and we're going to revisit that today. And then regression is basically a line of best fit. A line of best fit. Now, what's funny is I remember being in, I think it was maybe chemistry in high school, and we had made a scatter plot, which we're going to revisit again today, from way back when, beginning of term. And so we'd made a scatter plot, and it looked something like this: y-axis, x-axis, and we had some points here. And back then, what we did was we said, okay, a line of best fit, I'm just going to look at it and say, hey, here's my line of best fit, maybe. Seems reasonable, right? But there are tools that we use, and so those tools are called regression. And so we're going to look at how do we build this line of best fit. It is a mathematical formula that, just in short, we summarize it quickly, that minimizes the distances between this line and these dots. Of course, that makes a line of best fit. And so if we make some connections here, right, I've got my y here, I've got an x here, m is the slope, right? Whatever's attached to the x is the slope, and b is the intercept, the y-intercept. But usually we just call it the intercept. We're never really interested in the x-intercept. Okay, so we're going to talk about just the components of regression, so line of best fit, and how do we get these values, right? And so why would we even want these values, right? And so one of the main goals that we're going to have with regression, so umbrella term, we usually drop the linear, and there are other types of regression, but mostly we just use linear regression, so we drop it. And so when I talk about fitting a line of best fit, I'll just call it regression, right? And so so when we're doing regression, then usually what we want to do is we want to use this line, right? It's my best guess, my point estimate. Sounds familiar, right? And it is. I want to be able to put in some unknown or some unseen value of x, right? And predict the value of y, right? And so regression um, is mostly used. There are other uses, but mostly is mostly used to predict, and I'm going to highlight that, to predict future values of y. Yeah. Now, when I say future, I don't necessarily mean future in time. I mean future unseen values, right? And so here, unseen values of y, uh, from some value of x. And so we'll talk about that. Some terminology that we need to, a refresher on before we can keep going is, okay, if we have two variables, an x and a y, right? Then one of those will be the response variable, and you can call it the dependent variable if you'd like, right? And so we've got lots of terminology here. The response or dependent variable. I got smushed there, but that's okay. I'll call it the response variable. And then what did we call the x variable? We called it the explanatory variable because I like that it has the x in there, and then that guides me and prompts me to put it on the x-axis. So the explanatory variable, or if you prefer, independent variable. I only mention that because depending on what textbook you're reading in the future, right, it's good to have those links, right? Or if you've taken a stats course before, then maybe, especially if you were in, I think it's biology that really sticks to dependent and independent. And so depending on where you came from, uh, you might use different terminology, but I use response and explanatory. Okay? And so what we want to do is, given some unseen explanatory variable, and so maybe I should kind of clarify this. Given an unseen explanatory variable, value, right? Those are values. We want to predict the response variable. We use the regression line to predict the response variable. Right? So we use it to predict y. Okay. Oh, and I guess I should mention, I took the weekend off, and so I haven't finished marking your tests, but that's on my to-do list. And so you'll have those by Thursday for sure. But as soon as I'm finished marking, you'll see the grades on Moodle. You might have seen I forgot to hide them on Moodle. I hid them on my end, but then I didn't hide them from you. I don't know. And so, but a lot of marks are missing there, right? And so overall looks really good, looks really promising. And so, but once I've marked them, then you'll be okay. There's a lot of marks missing. Okay. I forgot to mention that. Sorry. Okay. So we need to develop this idea. Okay. And so we're going to learn to quantify the relationship between two numerical variables. Okay. So x is numerical and y is numerical. In fact, we'll be able to as long as we have a numerical response variable, then we can use either a numerical or a categorical explanatory variable. And so we'll see that. But generally, I don't want to highlight this whole thing here, maybe. But I will highlight that the response variable has to be numerical. Okay. And so y must be numerical. Most often, x is also numerical, but it's allowed to be categorical, and we'll see that. But we're going to focus on numerical response variables. And I will say on the final exam, it will be numerical as well, because the categorical variables are a little bit hard to read sometimes. Takes practice. So we're going to start with an example. And of course, we've got this scatter plot, and we're going to talk about the relationship between high school graduate rates in all 50 US states and DC, which is not a state, and the percent of residents who live below the poverty line. And so that's been defined as income below $23,050 for a family of 4 in 2012. So obviously quite outdated, but this is the data that we have, so that's fine. So first thing that we would need to do is we would need to identify, okay, what's the response variable? From the scatter plot, it's the percentage in poverty because it's on the y-axis, right? And so here, because it's on the y-axis, then I know that it has to be the response variable, right? Same thing here. Because the percentage of high school grads is on the x-axis, it has to be the explanatory variable, okay? Now, it's not always this easy. I'll give you a scatter plot. I think I give you the scatter plot on the final exam, so then you can grab the information from there. But yeah. I'm committing to that now. So you'll have a scatter plot like this with the variables labeled, and then from there, you're expected to know that the one on the y-axis is the response variable, and the one on the x-axis is the explanatory variable. Now, if you didn't have this, if it was just a blurb like this, then you would have to say, okay, which one do I want to predict? Right? So one of the variables is just explaining the response variable, right? But the response variable is the one that we want to predict. It's not always obvious which one we want to predict. In fact, you could argue, okay, if I want to predict the percentage in poverty from the percentage of high school grads, that makes sense, right? What if I want to flip it? In this scenario, right? There's no rhyme or reason here in this scenario. What if I want to predict the percentage of high school grads from the percentage in poverty? That's perfectly reasonable. It's not what we have here, but we could do that. Okay, and so the response variable goes on the y-axis. Okay? When we have a scatter plot like this, we always want to describe the relationship. And one of those reasons is because unless it looks like a straight line relationship, we're not going to be able to model it. So of course it's going to be linear, but we have to say it's linear. So here, and you just kind of need to squint a little bit, right? Is there any other shape except a straight line that would make sense here? Not really, right? If I kind of put my blinders on, looks like it goes in a straight line pattern, right? And so this is what makes it linear. Yeah. Three things. There are three things we need to touch on to describe this relationship. So whether it's linear or non-linear, okay? Maybe I'll put it on the previous slide here. So given a scatter plot, I feel like I need to explain more than that next slide does. We need to describe the relationship. Oops. First thing is linear versus non-linear. We've seen that before, right? With the shape center spread of a normal distribution or any distribution, right? Now we have two variables, and so a little bit more work, but we're just going to classify it as linear or non-linear. All the non-linear stuff we're not going to deal with in this course. That would be a second or even a third course in statistics. And so we're not going to worry about that. The second thing we're going to talk about, so a linear relationship looks like a straight line. I don't think I need to show that actually. Because a nonlinear relationship is anything that doesn't look like a straight line. And so there's lots of different options, right? Exponential distributions, that kind of thing. Next thing, I'm trying to remember if I have like a shape center spread where it prompts you. I don't think so. Linear, strong or weak relationship. Now the strength is I classify it as strong or weak. You can add things like moderately strong, right? Moderately weak if you want to. And again, it's kind of field specific. So I know psychology has it broken up by I think there's like 14 different slots that you can go into, and I've just made 2 now. So here, to clarify, if you see a pattern, I would call it strong, right? Or moderately strong. If you see a pattern, it is strong or moderately strong. If you don't see a pattern, if it's just a cloud, then I would call it a weak relationship. And what's that referring to? Right? If you just have a cloud of information or a cloud of data, then it really doesn't matter what value of X you put in. The prediction for your Y is going to be weak, right? And so that's where that's all coming from. And so the third thing is whether it's positive or negative, right? And so it's positive or negative. And a positive relationship looks like this, right? Both values are increasing together, whereas a negative relationship looks like this, right? And I like to put a little arrow on here just to show that, to emphasize that one's going up and one's going down, right? And so if we had to describe this relationship here, we said, okay, I see this pattern, this general pattern. Notice how I cut some out. That's okay. It's just for broad strokes. Okay, so I have a linear relationship. They say it's negative, right? And so here we've got this negative relationship. It's linear. And then I see a pattern, right? It's not very, very strong, and so that's why they've gone for moderately strong, right? But I see a pattern, and so so then I would call it moderately strong. We see a pattern, right? So then it's strong or some version of strong. Okay, nice. So just like how it was important to be able to look at a distribution, a histogram, for example, and talk about the shape and the center and the spread, and a lot of our analyses hinged on the shape-centered spread of a variable, right? And so now those are some things that we need to look out for, right? Is it a linear relationship? That's the most important thing. Is it positive or negative, right? How are these two variables interacting? And then is it strong or is it weak? Yeah. So if we fit a line, and these slides jump in and just give you the equation of the line so that we can talk about it. Okay, and then we'll talk about how we found these values. So of course we're going to have to find these values. That's our job, but software will do it for us very easily. And so that's why we're kind of jumping in here and talking about the interpretation. Okay. And so the linear model for predicting poverty from high school graduation rates in the US is this. Now notice here, the percentage in poverty is your Y, and Y hat, right, is the predicted value of Y. Y hat is the predicted value of Y. Okay. So when you put a hat on it, now we've seen p hat before, that's the sample proportion. But in this case, context will tell you that, okay, this is a regression question that has nothing to do with my p hats anymore. And so now, right, the hat becomes, it makes it a predicted value. Okay. So 64.78 minus 0.62 times the high school grad. Now, the high school grad, we already said, is your x variable, right? And so here, this is your x, and so you've got negative 0.62 times x. And negative 0.62, let's see what color I haven't used. The slope is negative 0.62. Because it's attached to the x, right? If we think about y equals mx plus b, right? Whatever's attached to the x, it actually doesn't matter which order it's in, right? You can have the mx first and then plus b, or b plus mx. Doesn't matter, it just doesn't have that same ring to it. And then the y-intercept, or the intercept, is 64.78. Okay. Now we're just given these values. We're going to see how to solve for these values later. Yeah. But what we said was, okay, our ultimate goal is to use this line to predict values, right? And so if we're told that the high school graduate rate in Georgia is 85.1%, what poverty level does the model predict for this state, right? And so this is a model that we've built. So this here, this equation here is the model. And what we can do is we can plug in some value of X, so some percentage of high school grads. And if you're not sure if you should be converting this 85.1 from a percentage, which is what we usually do, to a proportion, right? In this case, we just leave it as a percentage because these values here are in percents. Okay, so you just match the scatter plot that you've been given, right? The scale on that scatter plot. So these are in percent, so we just leave it as percent, right? So here, 85.1 stays 85.1, and we take it, what can I? 64.78, that's your y-intercept, minus the slope times 85.1 becomes 12.018. Now, it's really important, of course, that you apply BEDMAS. So you have to multiply before you can subtract from the y-intercept. Okay, and so that's important. But this is the predicted high school rate in Georgia. This is the predicted, the predicted percentage poverty in Georgia. So this is your y hat. So this is what we would have predicted using this line. And so, but we also know that we had information on all the US states and DC. And so what we can do is we can find residuals. Okay, so the residuals are exactly as they sound, right? Let the name guide you. They're the leftovers from the model fit. And so what we're going to have is we're going to have our line, right? So this line, we can plug in any value of x and find the value of y, the corresponding value of y. And I think if we had 85.1, do I have, oh, they're not showing they're not showing Georgia, but I guess it would be maybe this one. Is this Georgia? Very close to the line. So here we have the observed dot. Now it's going to be easier if we talk about this one, right? And so here we have this observed dot. That's the data point that we have. And then we have the predicted value at that point, right, is some value of y. You can trace across this way, right? Now the distance between those 2 points is the residual, okay? And so the data is the fit plus the residual. And so from the line, you move up or down some residual amount, right? And that's the data that you saw. I think the easier way to think about the residual is that it's the difference between the observed y and the predicted y at that point, right? And so y hat, so yi minus yi hat is the residual. The error or residual is the E. Yeah. So E came from the error term, right? How wrong is your line? You can think of it that way. We call it a residual just because it emphasizes what it is, right? It's the distance between the observed and the predicted value of y. So as an example, here, if we look at DC, we had this observed value of y, which was, I don't know, looks like 17 point something, right? And at that same value of x, right, we can predict the value of y, and we get, I don't know, it looks like 11 point something high, right? 11.5, let's say. And what we're going to find is that from the observed minus the predicted, then we get 5.44. Notice that this is positive, right? Because the observed is larger than the predicted. So if a point is above the line, then I have a positive residual. If a point is below the line, right? So if the observed is less than the predicted, then I'm going to have a negative residual. Okay? And so we can summarize that in terms of more or less than the predicted value. Okay, so what the line does, I'm skipping ahead a little bit here, but what the line does is it minimizes those squared residuals. Okay, and we're going to square them because otherwise, if I add these all up, I'll get to 0 just because of how the line was made. Okay, and so we have to square these so that we can add them up, and we've seen that before. Okay. Correlation is one of those terms that we use just in everyday speech, right? And so, oh, there's a correlation there, right? And what does that mean? A correlation means that there is some association or a relationship between two variables. Now, technically, the correlation describes the strength of a linear relationship. Association or relationship between two variables. Okay, and so correlation describes the strength. The idea of correlation is what we're using when we use it in speech. Oh, there's a correlation between those two things. Well, it means that there's a strong relationship between these two things, but we have to specify that it has to be linear, right? And so the way we use it is not technically correct, but it's the same idea. Now, correlation takes values between -1 and +1, where it crosses 0. There's no linear relationship. So here, from -1 to +1, and so what we're going to have is we're going to have no relationship, which looks like just a cloud. Okay. If there's no relationship between two variables, it doesn't matter what value of x you plug in, you're going to get the same value of y as your predicted value, right? Because it means that the line of best fit would just go straight through and have a slope of 0 eventually. Whereas if here we have a negative relationship, and it's a perfect negative relationship. And so here, this is a perfect, negative relationship. It has to be linear, right? And so what would that look like? It would look like this. Bink, 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 bink. Okay. They're all exactly on the line. Yeah. And the line of best fit would go through every single one of these. Bink. Oh, kind of hard, but they're all on that line. Maybe I'll draw these bigger. There's no deviation from that line. Okay. Obviously, going from a perfectly negative relationship to no relationship at all, there's wiggle room in between here, right? Where it goes maybe like this. Right? It's a negative relationship, but the points are kind of a little bit looser as we move towards no relationship. Okay. What about a perfect positive relationship? Well, that would look like this. I'm going to draw my line first. Has to be positive. And if it's perfect, all the points are exactly on that line. And then the wiggle room is here. Right. General direction like this. Right. Maybe I'll make it more clear like that. Well, And so at some point here, we're going to transition from a strong relationship into weak relationship territory, right? And so here, kind of around negative zero point 0.5 and roughly positive zero point 0.5. Now, I just use these as a guide, right? So if you have a correlation value, then you can look at that value and say, oh, it's strong or it's weak or moderately strong, moderately weak, that kind of thing. And so let me just move this a little bit closer here. So here, between negative zero point 0.5 and 0.5, I would call it weak, right? Just generally weak, no real relationship. Okay. Whereas here, kind of 0.5 to 1, here I have a strong positive relationship. And here, from negative 1 to negative, or yeah, negative 0.5, I have a strong negative relationship. Okay. And so that's the general layout of the correlation. Now, I will highlight again that the relationship must be linear. The problem is we will always be able to calculate the correlation, okay? But it only applies if it's linear. Okay? That's the same as we will always be able to calculate the mean, but it only applies if I have a normal distribution, right? Or it's only really useful if I have a normal distribution. And so it's the same thing. So we will always be able to calculate the correlation, but it only applies, it only applies as a measure of strength for a linear relationship. As a measure of strength for a linear relationship. That's really important. Okay. So, just to warm up here, if we have this relationship that we have in our example, right? So the percentage in poverty, the percentage of high school grads, which of the following is the best guess for the correlation between the percent in poverty and the percent in percentage high school grads? And so immediately we can eliminate some of the options, right? Remembering that, okay, it has to be, so the correlation has to be between -1 and 1. So immediately E is out. You can't have a correlation between that's negative 1.5. You just can't. The rest of these are between -1 and 1, so we need to keep working. I know I have a negative relationship, and that's reflected in my correlation. And so all these positive relationships, they're out. Yeah. So now I'm choosing between a negative 0.1 and a negative 0.75. Now remember, if it's negative 0.1, that's really, really close to 0, right? And so that that would just look like a cloud. Okay. And so here I can see a relationship which tells me that it must be this one. Okay? So this is what a correlation of negative 0.75 looks like. And that's why I say as soon as you see a pattern, right, this isn't as strong. Oh, I guess I could use highlighter. It's not as strong as maybe you would like, right? But it is strong enough to see a pattern, and at that point, we call it a strong relationship, and this is a relatively strong correlation, right? Okay, that's just the answer. just another example of doing the same thing. Okay, let's see here. We've got the percentage in poverty again, but now we have a new explanatory variable, the percentage of female householder, no husband present. And so just another variable that they've collected that they're interested in. And here, we don't really see a relationship. If I had to, right? If I had to, I would say maybe something like this. Maybe it's positive, right? I don't know. But it's quite weak, right? And so because I have this feeling that it looks a little bit positive, right? Just because we've got these upper points here and points down here, kind of anchoring at both ends. And so what I'm going to do is I'm going to eliminate now. I'm not really sure about this one. I'm going to eliminate those two, right? Because those are negative and it doesn't look negative to me. But if I had to kind of put bounds on here, right, maybe something like this. But I don't really see a pattern, right? If I saw a pattern, it could be 0.5 or 0.9. But in this case, I don't really see a pattern, right? And what I mean about that is, can I move this like this? I wonder. Could I have just as well put the line like this? Sure. Could I just as well have put the line like this? It'd be weird, but okay. Right. Could I have put it like this? Sure. Right. And so for that reason, that makes a weak relationship, right? Where it's not obvious where this line would go, right? And so that's why I put a little question mark here saying, kind of, maybe, something like that, right? And so I would say maybe 0.1, right? Because we don't see a pattern. Hopefully I'm right. Oh, I'm not. I feel like I am though. 0.5. I guess it's like this. Sort of see a pattern. I'm gonna remove the evidence. I'm gonna stick with my 0.1 because I want to show you guys what it looks like. I'm gonna delete that slide. Because I can do that. Remove the evidence that I was ever wrong. I disagree with the 0.5, that's why. Let's remove these. Which of the following of the four has the strongest correlation? Okay, and so the strongest correlation would be a correlation closest to -1 or +1. Now, A is a really strong relationship, right? But it's not linear. So if you had to think about it this way, right? The correlation measures how close the points are to this hypothetical line. Now, here, right, here and here, these points are very close to this straight line, right? But the rest of the points are very far off. And so although this is a very strong non-linear relationship, right? And so here, this is a strong non-linear relationship. The correlation wouldn't be strong because it talks about how close the points are to a line. And so here, right, all those points are nice and close to a line. And I guess this is a better example of a weak relationship, right? Maybe something like that. Or like we said, this line could probably look something like that, and it wouldn't even matter. So that's a weak relationship. This looks like a linear relationship, but it's weaker than B. So here I'll use B. Okay. Just as a note, the correlation is denoted by R, okay, by a lowercase r or a capital R. Okay. I use a lowercase r, okay, but the textbook uses a capital R. I understand why they do, but I just can't shake this habit of using a lowercase r, and so you'll have to put up with me. Um, it's okay, you can use either one, but I use a lowercase r, and the textbook uses a capital R. So here, Emily versus the textbook. Oops. It's actually more common to use a lowercase r. I I appreciate that it's clever to use the capital R, but it's more common that we use a lowercase r. So that's why I do. Okay. Good. Let's see what time it is. Okay, nice. Good. This is section 8.2, and I'm realizing I didn't put the section, but obviously it was section 8.1 that we started in, just kind of introducing these concepts of, okay, if we have a scatter plot, there's a relationship there. Can we describe that relationship? And then can we have a numerical measure of the strength and the direction of the relationship? And so here, maybe I'll put it here. Or maybe I'll just continue. The correlation is a numerical measure of the strength and relationship, or the strength and direction. The correlation is a numerical measure of the strength and direction of a linear relationship. Okay. Thinking back to the normal distribution, so if we had a scatter plot, or sorry, a histogram, then we could look at it and we could talk about the shape, the center, the spread of that distribution. And then we said, okay, if I have a normal distribution, then the numerical measure of center is going to be the mean. The numerical measure of spread is going to be the standard deviation. And so the correlation does the same thing, right? We talked about whether it was linear or nonlinear, and we're not going to touch nonlinear. And so if it's linear, then I have this numerical measure of the strength, right, and the direction, positive or negative, in the correlation. So that's nice. Okay, so if we want to fit a line, and it's called least squares regression, but we're just going to summarize it and call it regression. This is the most common regression equation that we could use, and it's the only one that we'll use because it's the only one that is used in most worlds. But what we want to do is we want a line of best fit. If you had to kind of take a step back and think about a scatter plot and think about, well, what makes a line of best fit? Well, that's going to be a line that has small residuals, right? Small distances between each of the points. And so we have a couple of options. Okay. Option one is to minimize the sum of the magnitudes. So minimize these residuals, the absolute value of the residuals. That's an option, right? Find the sum of these absolute values that's the smallest, and then that's your line of best fit. What if we had to, so the problem with the errors or the residuals is we saw some of them were positive and some of them were negative depending on where around the line they are, right? And so if we were just adding them up, they would just add to 0. And so then what we do usually is if we're adding things up, we take the absolute value or we square them so that I get only positive values, right? Squaring a negative value makes a positive. And so option two is to minimize the sum of the squared residuals, the least squares. And so that's where the least squares regression line comes from that we use. And so here we use this. And so we're going to minimize the sum, so adding up all of these of the squared residuals. Yeah. And we use it because it's the most commonly used. It's easier to compute, which was, of course, a huge selling point before computers, right? And so that would be nice, right? And it has this added benefit of, okay, if I have a large residual, right? Then if I square it, it becomes even larger, right? And so here, if I have, for example, a residual of 1, so EI squared, you can ignore each of those subscripts, the i's or the 1, 2, 3. It's just for each data point, right, has one a subscript. And so if I have a residual of 1 versus a residual of 2, right, that this is twice as large as the first one. Okay, what happens when I square it, right? 1 squared is 1, but 2 squared is 4. So notice that this was a change in 1, but this was a change in 3, right? Moving from one to the other. And so that's what we mean here. A residual twice as large as another, so 2 is twice as large as 1, is usually more than twice as bad. So here we're saying that's three bad, if you want to think about it that way. And so so that's why we use the square. Yeah. Some theory. Y hat. So the least squares regression line looks like this. So we have a y hat, which is the predicted value of y. We've already seen that. Technically, we have betas here, right? But we saw y equals mx plus b. And if you're comfortable with that, then that's fine. But technically the parameters, remember, so here we've got some data set. So we're still working in that inference realm of, okay, I have a data set, I have a sample, right? But I really want to know about the entire population, which I don't have information on, and that's fine, right? And so the population has some intercept, beta naught, okay? And here, beta Greek letter beta. Beta naught is the intercept, and beta 1 is the slope, and it's attached to the x, which is the explanatory variable. Okay. So we're going to have some parameter beta naught, but we're also going to have a point estimate, just like we did before. Now, what's fun about this point estimate is it does have some standard error, just like we're used to, but it'll just be given to us, so we don't need to think about what it is or where it came from or anything. But it's a spread around the point estimate, just as it was before. You can do inference around the intercept, right? And we can And we can build confidence intervals around the intercept, right around this point estimate. They're not usually that interesting because it is the intercept, but we can, and that's the fun part. We're usually more interested in the slope, right? And so we have this slope, this point estimate for beta 1 is b1. And so what our equation is going to look like is y hat is b0 or b naught plus b1 times x. Okay. And that's our point estimate of the line, right? Or our point estimates. So what we will be working with is this line here. Okay. What is fun is we can do inference around the slope. So if I have a point estimate for the slope, then what's something that I could be interested in? Well, I might want to know, is the slope significantly different from 0? Thinking about what a slope of 0 looks like, right? It's just straight across like this. And it means that there's no relationship between these two things, right? And so we can do inference around the slope, but we'll see if we have time for that. Usually we don't have time to dive into that, but might be nice to see one or two examples. But first we need to talk about the conditions for the least squares regression line. And so of course, if I'm fitting a straight line, it should have a linear relationship, right? And so it should be best described by a straight line. Okay. The second condition is that the residuals, so notice how we're able to calculate the residuals for each data point, which means that now I have a sample of residuals and I can make a histogram of that, and it should be nearly normal, centered on 0. It doesn't say that, but nearly normal residuals. I'll add it. Centered on 0. And kind of the tricky one is we need to have constant variability, okay? And there are slides that follow, but I'm just going to draw them here. So the linearity condition, we need to have a straight line, right? And so we need a straight line relationship, so that's what linearity means. We need a straight line relationship in order to fit a line. A straight line model. I'll start throwing that term, sprinkling that term in model, okay, because that's what the line is. Okay. For the nearly normal residuals, the residuals we can calculate, calculate the residuals, the residual for each point, then make a histogram. And it should look something like this, centered on 0. And for the third condition, the one that I really wanted to be talking about here, is constant variability around the line is what that's really talking about. Oh, it's lagging. There. Okay. And so I'm going to show you what it looks like if you don't have constant variability. Or let's do one versus the other. Constant variability. You've got a line, and you've got essentially just kind of even scatter around the line. even scatter around the line. Whereas if you have non-constant versus non-constant variability, oops, if your line looks like this, right? Let's say you have really, really tight, maybe it looks like this, right? And so here, these predictions are very strong, right? You're very confident in these predictions, but then you're using the same line for predictions in this realm, right? And so that's going to be a problem, right? And so that's where the non-constant variability, or what it looks like, right? And so we need to have random scatter around the line. And these next few slides just kind of talk about how do we assess these conditions? We assess them using a residual plot. And so usually what we do is we take the residuals um, and da, 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 um, this, maybe I'd want to do this instead. The residual plots are these ones here, where you plot the residuals on the y-axis, residuals, and the explanatory variable on the x-axis. And so then what you're looking for is random scatter around 0. Now, I'm not going to focus too much on these residual plots, but we do use them as kind of a magnification of the original relationship. So whereas here we have the response variable against x. So the residual plot basically magnifies. So notice where it's most obvious here is we have this kind of non-linear relationship. And when we look at the residuals against x, then it's really magnified. The residual plot magnifies the original scatter plot. We want random scatter around 0. So here, this is 0 in each of these, of course. We want random scatter around 0. So here's a residual plot. So the anatomy of a residual plot. Here we've got the original scatter plot, right? And so we can find the residual negative 4.16, well, at that same value of x, right? We've got that residual negative 4.16. And for DC, we had a positive residual at 5.44. So it's up here, and we can plop it down 5.44 as the residual. And so that's what we mean by we want random scatter around 0 here. I don't test the residual plots on the final exam. It will be on an assignment, but it's not on the final exam, and so that's why I'm kind of floating through it. Right. On the assignment, you'll have the notes to refer to and the internet and each other and me, and so I'm not too concerned about that. Yeah, so we can make a histogram of the residuals. If it looks approximately normal, centered on 0, then that's great. We're good to go. Oh, just for a fun word, hard to say, but the constant variability is also called homoscedasticity. Homoscedasticity. Oy. I mention it because I am pretty sure that there's an assignment question that asks about homoscedasticity, and so that's why it's good to know, but it's this constant variability condition. Homo, of course, means the same, and then the scedasticity is the variability. Blah, blah, blah. You can try those on your own, but we've already talked about it. Okay. We need to be able to build the least squares regression line. That's why I skipped to here, because it's the most important part for today. We need to be able to build the least squares regression line. Which looks like this. Y hat is B0 plus B1x. Now, this is where we're going to go to your formula sheet, because of course it's on there. If I have it, plop it in here. Okay. 2 sample means we did last Monday, right? That's where we kind of finished our confidence intervals, hypothesis testing, and now I haven't even brought in the formula sheet because I'm not going to make you do this calculation. It's crazy. Maybe with this one, but probably not. Here, the correlation. Let's talk about this one first. SXY. SXY is the covariance. I only mention that because it might be part of the information that you're given on an assignment. And so you won't have to calculate it, right? Because it's the sum of the xi's minus x bar times yi minus y bar, and then divided by n minus 1. Here's an alternate way that you can calculate it. You don't need to worry about that because there's a covariance command in Excel, so you're fine. There's also a correlation command, but this is where, so this is maybe the version of finding the correlation that I would get you to use, okay? Of course, there is this bigger formula, but you can just ignore it. And capital R, lowercase r, they're used interchangeably, and I use the lowercase r. Okay? So, if I have an x here, right? The percentage of high school grads is a column in my Excel spreadsheet. I can find the mean, right? I can find X bar, and I can find the standard deviation of X. Now we use a little subscript X because we're also going to have the standard deviation of Y, of course. And so here, this is your Y variable, which means I can find the average percentage in poverty and the standard deviation of Y. And so notice we've got 2 pieces of information for each of the variables. And so the mean and the standard deviation for each variable. And then we're also given the correlation, which gives us the strength and the direction of a linear relationship. And so this information is all we will need to be able to build this regression line, which brings me to the formula sheet again. And it's the last part of your formula sheet. I know it felt like you'd never get here, but here you are. You did it. Well, we're not done yet. It's not over till it's over. But what does that mean? It means that I'm not introducing anything testable past this, right? Just concepts, no formulas. So here, your least squares regression line, y hat is b naught plus b1x, right? So it's on your formula sheet. And what I want you to really practice reading is, okay, so if you're not sure which one of these is the slope, I tell you what the slope is. The slope is b1, okay? And how we calculate the slope is we take the correlation times the standard deviation of the y's divided by the standard deviation of the x's. Okay? And then the y-intercept, b naught, relies on the slope. And so it's a little bit backwards feeling, but then you look at the formula for the intercept and you see, okay, I need the slope, so obviously I need to find it first. And that's why it's listed this way on your formula sheet. Okay, and so B1 goes in here, and so, right, once you've found it, then you can find the y-intercept. Yeah. So the slope is the correlation, which I'll give you in one way or another. Right? Might make you calculate it using that simpler formula. Probably not. And then times the standard deviation of your y's divided by the standard deviation of your x's. Now, this is where it's really important that you don't mix these up, right? 1/2 is very different from 2 divided by 1, right? And so you want to be really careful. And so then your intercept, your y-intercept, is y bar minus b1 times x bar. And then the residual is your observed minus the predicted y, or if you prefer, yi minus yi hat. I don't have that on your formula sheet, but you could add it if you wanted to. Okay, and so what I want to do is for Thursday, of course, it's in the rest of the notes, but for Thursday, calculate the slope and the intercept. So I want you to try it on your own. You've got all this information. Try it on your own, see how it goes, and then we'll pick up there as review on Thursday. If you have any questions, let me know. Otherwise, I'll see you then.